Alright, people, let's talk about tangent and cotangent. So we can think about generally in trig, we've got our three basic sets of functions here, sine, cosine, and tangent. Today we're going to talk about tangent and cotangent. Cotangent generally just the reciprocal, sort of flipped around version of tangent. So whatever applies to tangent will generally apply kind of in a reversed way to cotangent. But to start, we're going to start with sine and cosine, which are a little easier to handle. So using our unit circle, I've got divided it into quarters. Let's fill out these values. So at 0, we've got our sine of 0, cosine of 1, pi over 2, sine of 1, cosine of 0. Starting to see a pattern here. And then it repeats over and over again. You can keep going around the unit circle. So, that should be a review. Little brain here. I'll probably put these in other notes. Just something to think about to get us started with this topic. So, I said if there exists a point of the graph y equals sine x and y equals cosine of x, so I guess two different graphs, where y equals 0 for some x, that being the angle, what can that tell us about the general appearance of tangent and cotangent? Now, tangent, we know from forever ago, is opposite over adjacent, so got TOA. So our opposite generally is sine and over cosine. So if there exists a point where both of these have a 0 value, as we've just highlighted in our table, if one of these is 0, that's going to cause a problem, right? So tell us about the general appearance of it. Now, we know when we divide by 0 in math, it's undefined. So we're either going to have some sort of hole or an asymptote. Because we cannot have a defined point when cosine is 0, and we know for a fact, up here, that cosine will be 0 at some point. So let's state the domain, range, asymptotes, period, all the good stuff. Let's graph it first. Generally, I don't need you to graph things in a really pretty way, so I'm just going to go with the basics. So we know that we need to find a point where cosine equals 0. So cosine is 0 at pi over 2, and it's also 0 at 3 pi over 2. So another way to express 3 pi over 2 is just negative pi over 2, because you can either go pi over 2, 2 pi over 2, 3 pi over 2, or you can go negative pi over 2 in that direction. So that also shouldn't be anything new, but I'm going to draw these dotted lines at negative pi over 2 and pi over 2, because we know that the value is not going to give us anything at these points, right? And if we investigate points close by, so let's say when we are getting really close to pi over 2, really close to, so I'm going to draw my unit circle in this crazy rainbow color. When we're getting really close to pi over 2 on our unit circle, this angle is getting really big. Our cosine, our x, is shrinking, and our y is getting really big. So it's y over x, or sine over cosine, and sine is getting really big, and cosine is getting really small. So we would imagine that this is going to get really big in a positive way. So really big in a positive way. And we know that we also, at 0, we have 0, because sine is 0, so 0 over 1 is going to be 0. So we have a point at the origin, so let's connect that. And then what's going to happen on the other side is pretty similar to this. So we know that at negative pi over 2, or 3 pi over 2, whatever flavor you prefer, we have a sine value of, it's going to be increasing, it's almost the exact same here. We have a y value that's getting really big, just getting big in the negative direction, and a cosine that's getting really small in the negative direction. So in that regard, we're going to have something like this. So kind of just mirrored over that axis. So domain, we've got negative pi over 2 to pi over 2. And this is going to repeat because you can keep doing this pi number of times. You can keep going around the circle. So our period, or how long, our period is how long it takes to repeat. So this is our domain. And our period we can extract from our domain, which is pi. The distance between these 2 points right here is pi, because we go pi over 2 on the right and pi over 2 on the left equals pi. We've got asymptotes at pi over 2 and negative pi over 2, and our range is negative infinity to infinity. Okay, so that's basics of tangent. And again, I want to repeat that this is not the only tangent graph. This continues on into infinity, that we have a bunch of these, because you can keep going around the unit circle and making larger and larger x values. Just keep spinning around the unit circle. So these will continue on in this direction and continue on in that direction. So you'll have these asymptotes as multiples of pi over 2. So let's move on to cotangent. If the points pi over 2 and 3 pi over 2, or negative pi over 2, are undefined for tangent x, where might we look for undefined points of cotangent x? So if tangent is opposite over adjacent, or sine over cosine, we get to do a switcheroo for cotangent. So it's going to be adjacent over opposite, or cosine over sine. So we need to find our undefined points. That's often the best place to start looking. We need to find where sine is 0. So we know that sine is 0. At 0, sine is 0. So we're going to have, let's go back a few, sine is 0. At 0, sine is 0. And at pi, sine 0. So we know that we're going to have undefined points at 0 and at pi. So let's sketch that out. First, I'm going to sketch out the without the 2, and then we're going to talk about the 2x for a second. So let's start with our asymptotes. So this is our graph. Asymptotes, we know that at 0, we're not going to have a value. So we have, I'm going to label this with a big colorful A, an asymptote here. And then we know that there's another asymptote at pi. So I'm going to draw that with this dotted line here. We've got an asymptote at pi. Now, let's investigate what's going to happen at at pi first. So at pi, I'm again going to make my unit circle over here. We're headed in this direction, and our cosine is getting big, and our sine is getting small. So we have cosine is getting big over sine is getting small, and we know that our cosine is getting big in the negative direction, right? Because we're on this left side of the unit circle, on the negative side. So we have a negative over a positive. So it's the magnitude is getting big, but in a negative direction. So we've got something getting big in the negative direction over here. And then where do we know that our value is going to pass through the x-axis? Where is x equal to 0? Let's take a look. So we need to find where cosine is 0, because it's going to be 0 over 1, is pi over 2. So at pi over 2, we will pass through the x-axis at pi over 2. And then, let's see what happens when we start to get closer to our other asymptote of 3 pi over 2, or excuse me, of pi, or of 0, excuse me, we started at pi. So when we're getting close to 0, so we're getting, going in this direction, and our cosine is getting bigger, and our sine is getting smaller, and they're both in the positive direction, it should be really big in the positive direction. So again, big magnitude, but in the positive direction. So that should look a lot like our our tangent graph. And again, all of these will repeat. So we've got this period from 0 to pi, we've got another period of pi, and this is going to repeat pi n number of times. Pi times n, meaning we can do n number of these squiggly guys with this same period. Now, let's briefly cover this. I realize this is going a little longer, but the 2x, so if we think about the period as the time it takes for the graph to repeat itself. So if we think about the regular graph of cotangent of x having a period of pi, are we going to get to this period of pi faster or slower if we have a multiple of 2x? Meaning, if I multiply whatever this angle is, say it's pi over 2, if I multiply that by 2, I'm going to get cotangent of pi. So I will have gotten to the period faster. You can think about plugging in pi over 2, and it's like, okay, I'm already at that period. So they should stretch out. The period should become shorter. The period should become pi over 2 in this case, because normally when you plug in pi over 2, we've got this value here of 0, but now when you plug in pi over 2, we've got an asymptote, because pi over 2 times 2 is pi, and we know that at pi we have an asymptote. So we're squeezing this up over here. So asymptote's going to shift over here. So multiplying by 2x is going to affect our period in the sense that we will achieve it faster, or we will stretch the graph in this vertical direction and compress it in this horizontal direction. Okay. I'm going to pause here and leave this for the Edpuzzle, expressing cotangent in terms of tangent. So I will leave you with one helpful hint. So this is our graph of tangent to review. This guy passes through the origin and has asymptotes at pi over 2 and negative pi over 2. And our graph of cotangent, I'm going to draw in gray, does not pass through the origin because we have this asymptote here, but looks generally really similar. We've got this x-intercept of pi over 2, our asymptote here, and our other asymptote at pi. Now, you need to do two things to this graph, two things to the graph of tangent to make it look like cotangent. So that's what you're trying to do in an algebraic form. I'll leave that as an open-ended question, and we will talk about it in class.